HPLC Column Fundamentals. The seminar HPLC Column Fundamentals provides an introduction to how solutes can interact with columns containing porous particles and stationary phases to result in separation. The efficiency, retention, and selectivity terms in the resolution equation will be explained, as well as how certain particle and column characteristics can alter the terms and affect resolution. It should be suitable for new HPLC users or those who have some experience and need a quick refresher on measurement and interpretation of column performance. The next slide illustrates the separation process on a column that is filled with porous particles. Sample is introduced and transported through the column by a mobile phase. Sample components interact with the stationary phase to different degrees and separate into pure zones that can be analyzed and or collected. The next slide shows the well-known resolution equation, along with a further definition of how the terms are calculated. In nearly all modes of HPLC, some form of selective retention by the stationary phase is required for column resolution. In order to know whether a compound is retained, one must determine the column void volume, V sub m or V0, by measuring the retention time for an unretained solute at a given flow rate. Once a column void volume or void time for a given flow rate is known, it will not change. If a solute elutes near or at the void, resolution caused by stationary phase interaction cannot occur. Most textbooks recommend that all peaks of interest be retained with a K of 1 or greater for reliable quantitation. A K of 2 to 3 is much safer if it can be achieved. A K of more than 10 does little to improve resolution, and it increases analysis time and dilutes the sample to make it harder to detect. Retention factor is sometimes also referred to as capacity factor, as shown in the next slide. It is a relative retention factor that defines retention in multiples of the time at which an unretained peak elutes, T0 or T sub m. This is also referred to as the void volume or solvent front for the column, which is the total liquid volume inside and outside of the column particles. The K value for an unretained peak is 0, and the K value for a peak that spends equal time in the stationary phase and mobile phase is 1. All solutes spend the same amount of time in the mobile phase and different amounts of time in the stationary phase. The column void volume in reversed phase mode is usually established by injection of a very polar compound, such as uracil or thiourea. Several different methods can be used to confirm true void volume. Once V sub m or T sub m at a given flow rate is established for a given column, it will not change. Selectivity or separation factor alpha is calculated from the ratio of K values for adjacent peaks. The K for the later peak is always placed in the numerator so that K values are always greater to or equal than 1. A good selectivity for HPLC is 1.1, which allows a resolution of 1.5 to be achieved with about 10,000 theoretical plates. The critical pair in a separation is defined as adjacent solutes which have the smallest alpha value. It is this value that defines the minimum number of plates needed to achieve a defined resolution, which in turn defines the minimum particle size and column length. Ultimately, it is selectivity that determines the speed of analysis. The next slide shows efficiency, N, or the rate of zone spreading, measured by taking a ratio of retention time to peak width and squaring it. When peak width is measured at half height, the constant is 5.54. If the peak width is measured at base, a constant of 16 must be used to arrive at about the same N value. Retention time and peak width must be measured in the same units in order for a valid column efficiency determination. The next slide shows that peak width can be increased and apparent efficiency decreased by the effects of band spreading due to laminar flow outside of the column bed. The effect on the sample zone is illustrated in the slide. The zone velocity is near 0 at the wall and twice the average velocity at the center. An open tube becomes an excellent mixer if the sample spends too much time in this environment. This has the undesirable effect of decreasing N and lowering resolution. Its effect can be minimized by making connections with very short pieces of small ID tubing. More care is needed with shorter columns and small ID columns. Extra column dispersion is often an area where two HPLC systems differ from one another. One system will usually show higher efficiency with the same column because it has a more efficient flow path from the injector through the column to the detector. Peak symmetry also affects column efficiency and therefore resolution. Strongly adsorptive or active sites are often responsible for tailing peaks. Columns may show high efficiency and resolution for neutral solutes and very poor efficiency and resolution for bases or acids. Solute tailing is often accompanied by additional retention, as shown in the two separations on similar stationary phases. In this example, the poor peak shape for bases is likely caused by the presence of too many acidic silanols for the active column. Excessive column activity for a particular solute is not necessarily a characteristic of an older column that has lost stationary phase. It can also be observed in new columns where the phase chemistry has not been optimized for that particular sample type and operating condition. A common method for calculation of peak symmetry is shown. The ASTM has recommended the back-to-front ratio of a bisected peak measured at 10% of height and has called this asymmetry, A sub S. A tailing peak has a value greater than 1, while a fronting peak has a value of less than 1. The USP has also recommended the back-to-front ratio of a bisected peak measured at 5% of height, and it called this the tailing factor, T. But the ratio is made by dividing the total width by twice the front width. Both calculation methods give the same value of 1 for a symmetrical peak, but the USP method gives smaller values for tailing and fronting than the ASTM method. If you use an automated method for symmetry calculation, check your data system to see which method is being used. Many data systems have both calculation methods available for selection. This next slide summarizes the resolution equation and how to improve resolution by making changes that can alter each of the terms. For example, if selectivity, alpha greater than 1, and retention, K greater than 2, are adequate, one should examine the efficiency term. The two best methods for gaining efficiency are increasing column length, N increases directly with length, and decreasing particle size, N increases indirectly with particle diameter. A combination of change in length and particle size may be optimum, or one can try to achieve even more selectivity. If peaks are tailing, the best way to improve N very significantly may be to reduce tailing by changing the column or operating conditions. Higher operating temperature and reduced dispersion volume can also improve the N term. Similar thought processes can be used for alpha and K when there is clearly enough column efficiency, very narrow symmetrical peaks, but a larger selectivity or retention term is needed. When the sample contains multiple peaks, this type of analysis is usually done for the critical pair, but remember that all peaks to be analyzed must be retained in order for the column to be working at all. The closer one operates to the solvent front, the greater the danger that coelution will occur. This next slide illustrates the types of substrate platforms that have been used for preparing particle-based HPLC columns. While commercial column examples exist for each platform, the most popular has been the silica particle. Purified silica is readily available in a variety of pore and particle dimensions and is amenable to chemical modification that changes mode and selectivity. The next slide summarizes the benefits and drawbacks of porous silica particles as an HPLC column platform. Benefits include mechanical strength, high surface area for retention, easy chemical modification, many surface chemistries to choose from, and many methods to select from. Drawbacks include variable pore structure that can cause lot-to-lot variation in performance, a reactive surface that can retain bases and cause tailing, and poor substrate stability at higher pH values. Both high-coverage silica particles and hybrid silica particles will show reduced column lifetime when operated above pH 8 to 9 for extended periods. Careful selection of mobile phase additives and other operating conditions can allow acceptable silica column lifetime at high pH, but it should be avoided when possible for best results. The next slide lists the main variables that affect an HPLC separation and method. For a given platform, such as silica, the particle size and distribution determines the column efficiency and pressure and flow characteristics, and the pore structure determines the uniformity of bonding and the ability of solutes to gain access to the bonded phase. And the surface area determines the amount of stationary phase and degree of retention for a small interactive solute. Reagents and bonding conditions have a lot to do with column performance. Two main types of reagents include monofunctional, where 1 mole of reagent reacts with 1 mole of silanol, and polyfunctional, where 1 mole of reagent can react with more than 1 mole of silanol and also another mole of reagent, depending on moisture conditions. These phases are called monomeric and polymeric, respectively. A second follow-on reaction with a smaller reagent is called end-capping. It is done primarily to reduce the amount of silanol interaction with bases and give sharper, more symmetrical peaks. All column particles with bonded phases are not end-capped. Separation mechanisms are determined by choice of bonded phase type and mobile phase. The RP mode or mechanism will receive primary emphasis. Column dimensions will not be covered, although they are a very important aspect of HPLC method development. The next slide shows the relationship between particle size and pressure. They are important variables that are being hotly debated in HPLC. The standard choice for HPLC methods has been a 5-micron particle for some time. This choice was arrived at for good reasons, as shown in the graph and table. With efficiency of 10,000 theoretical plates, a 10-centimeter column with 5-micron particles delivers sufficient performance to solve many separation problems, and the pressure requirement is very low at about 50 bar or 750 psi. More plates can be achieved by using smaller particles. However, the cost is high in terms of pressure. At high pressures, both column and system failure become more of an issue and can affect method reliability. We have noted earlier that efficiency is directly proportional to column length and inversely proportional to particle diameter, but resolution is only proportional to the square root of n. Since pressure required for a given flow and column dimension is inversely proportional to the square of the particle diameter, this can be an expensive way to achieve increased efficiency. Operating at elevated temperatures can reduce flow resistance by reducing mobile phase viscosity. Sample stability is seldom an issue for moderately elevated temperatures up to 100 degrees C because solutes are on the column for such a short time. This next slide illustrates the importance of pore size in determining retention. Only a few % of the total surface area for a porous particle lies outside of the pores, so a solute must penetrate the pores in order to be adequately retained. Small molecules with molecular weights up to about 1,000 are relatively free to diffuse into and within the pores of even 100 angstrom pore size particles. Most drugs and other industrial chemicals are small enough to gain access to nearly all of the internal pore structure of the packing. When larger molecules approach the size of an average opening in the particle, they experience restricted access, which reduces retention and causes broad peak shape, low efficiency, and poor resolution. When sample molecules are comparable in size to the pores, poor recovery is also often noted. Larger molecules are usually separated on columns with particles having larger pores in the 200 or 300 angstrom range. Very large molecules may require particles with even larger pore sizes, although they can lose the benefits of mechanical strength. The chromatography can be greatly influenced by pore size and surface area, as shown in this new slide. Since small molecules, molecular weights less than 1,000, are free to move within the pores of both small and large pore packings, the K values are directly proportional to surface area and inversely proportional to pore size. Pores of 100 to 200 angstroms are typically selected for separation of small molecules. The next slide shows the same effect by measuring column capacity from breakthrough volumes obtained by running a dilute sample solution through the column to determine its saturation point. The appearance time of the sample corresponds to the retention time for that component if it were injected as a small sample rather than a front. Although 150 by 4.6 millimeter columns can hold 20 to 40 milligrams of total sample, only about 5% or 1 to 2 milligrams of that amount can be introduced under good chromatographic conditions. When larger molecules are introduced, retention and capacity decrease due to restricted access to surface area within the pores. At some point, retention on small pore packings crosses over that of larger pore packings, making 200 or 300 angstrom particles preferred for large molecules or samples where both large and small molecules are present. Chromatograms in this next slide confirm that retention of small molecules is shorter on small pore packings. Both retention and peak shape are improved on 200 and 300 angstrom packings. Another way to illustrate the pore size effect is a graph of pore size versus column capacity in terms of milligram per square meter. In each case, the larger molecule shows less access to the surface area than the smaller one. Only with a 300 angstrom packing do both molecules have comparable access. This new slide shows several important HPLC separation modes. If molecules can gain equal access to the surface area inside the pores, the degree of stationary phase interaction determines retention, selectivity, and resolution. Three important HPLC separation mechanisms or modes. Reverse phase has become the most important and widely used HPLC technique. The illustration in this new slide shows a monofunctional organosilane reacting with silica gel to form a stable siloxane bond. Although substrates can be used uncoated, the most important HPLC columns employ porous particles that are fully coated inside and outside with stationary phase. Bonding reagents are generally small enough to react with nearly all of the silica surface. However, larger reagents, such as C18, may require end capping for complete coverage. Monofunctional reagents are popular in part because they are highly reproducible. Polymeric reagents employ multiple reactive leaving groups and may be employed to add extra stability or special shape selectivity to the stationary phase. Two examples of popular monofunctional bonded phases are acenis C18 and C8, as shown in the slide. Both have high phase loading and are very retentive for solutes in a reverse phase mode. A typical bonded phase surface is shown in this next slide for a monomeric C18 column. As stated previously, end capping can be more important for larger bonding reagents such as C18, phenyl, and others because they may not cover the silanols as well as smaller reagents such as C8. Some C8 phases are not end capped at all because the extra step does not improve performance significantly enough. End capping reagents are typically small and also monofunctional. Silanols normally add complexity to the retention mechanism and can cause tailing with basic compounds under certain mobile phase conditions. C18 columns have become the industry standard as suggested in this slide. The hydrophobic interaction forces that are dispersive in nature are often sufficient to allow C18 and C8 columns to retain and separate many organic compounds. However, results may not be optimum in all cases. Trial and error has shown that selectivity, retention, and efficiency can all suffer with certain sample types. The next slide suggests that modern C18 and C8 columns are becoming much alike due to evolution of silica particles and development of improved bonding chemistry. Changing from a C18 to a C8 or from one brand to another may not produce a different, better result. When resolution is not acceptable for any reason, an alternate stationary phase with more polarity than C18 or C8 may be the answer. The remainder of this seminar will be an introduction to how the stationary phase can play a unique and important role in changing retention and selectivity for certain classes of compounds. Similarities and differences are easily shown by plotting log K values for a test mix with two columns under the same conditions. If there is a high degree of correlation, a straight line with low standard deviation, the two columns have very similar selectivity. If the test mix and the sample of interest contain similar compounds, there would be little reason to evaluate both columns. If only a very slight difference in selectivity is needed, Evaluating both columns may still be successful. Modern C18 columns have become very similar in selectivity, even for basic compounds, because silica quality and bonding techniques have improved to the point that silanol effects are minimal. The main reason for looking at two C18 columns would be for improving peak shapes and gaining a minor change in selectivity. Even if successful with one C18 over another for a difficult separation, lot evaluation should be conducted early during method development. The next slide describes some types of chemical interaction that can occur between sample and stationary phase. Nonpolar solutes with alkyl character will usually be retained and separated best with alkyl phases. If a separation looks promising on C18 but still requires optimization, small changes in the mobile phase should be investigated. Changing to a C18 column should also be investigated. Polar solutes may be retained and separated better on a stationary phase that includes some built-in polarity, such as an amide, phenyl, or pentafluorophenyl phase. Ionic solutes may require phases having ionic character for best results. It is important to appreciate that complex molecules can interact by more than one mechanism, making it difficult to predict results without injecting samples. In this introductory seminar, we will briefly describe some types of polar interactions that can occur with amide and phenyl columns, and show some examples of improved retention and selectivity over C18. A comparison of selected Sapelco columns is shown in the next slide. The first four columns are designed for use in reverse phase methods with small molecules. Asenis, RP amide, and phenyl fall into a category called polar RP phases, which should be tried when C18 and C8 are inadequate, which may be as much as 25 to 50% of the time. Asenis silica should only be used for normal phase or aqueous normal phase when reverse phase methods fail. Discovery HSF5 pentafluorophenylpropyl can be employed in either reverse phase or normal phase modes as a unique phase that often solves very difficult separation problems. That solutes which are very hydrophobic and contain mostly carbon typically show maximum retention and selectivity on C18 and C8 columns, as seen for some simple aromatic molecules. Note that aromatic character alone does not make the two aromatic phases more retentive, so the rule of like attracts like does not apply. It is more often differences in chemical structure that create molecular interaction, retention, and separation. When even small molecules have a polar functional group, such as nitro, hydroxyl, amino, and many others, the phases with built-in polarity and polarizability can show better retention and selectivity as shown in this next slide. Note that this is the case for the simple nitroaromatics. The extra retention for phenyl and PFP are believed to be due to formation of strong pi-pi complexes between solute and stationary phase. Nitroaromatics are pi acids, while the phenyl phase is pi basic, which can help explain the stronger attraction. Note that C18, C8, and RP amide are about equally retentive, which suggests that the interaction is coming from the alkyl chain and is mainly dispersive in nature for these compounds. The data in the next slide clearly show that RP amide is more retentive and selective for catechols and resorcinols under these conditions. The phase that contains an ether group is only slightly different in retention and selectivity from a straight-chain C18 phase, because ether does not have the ability of an amide group to hydrogen bond with phenols. Although comparing an ether phase to a C18 phase may be useful if only slight differences in selectivity are needed, the most dramatic results for phenols and other acids will be obtained with phases that contain an amide group, such as the Asenis RP amide. In the next slide, enhanced retention for aromatic compounds, especially those containing heteroatoms in and near the aromatic ring, is shown for Asenis phenyl compared with Asenis C18, Asenis RP amide, which has an amide embedded in a long alkyl chain, and another phenyl phase that has about equal amounts of alkyl and aromatic character. We can draw several conclusions from this data. Since Asenis C8 and RP amide behave so similarly, it is clear that the amide group does not interact much with either molecule, and interaction seems to be mainly between the alkyl chains and the drugs. The acenis-phenyl phase attracts and retains buspirone more than trazodone, which must be a result of strong pi-type interactions which are not possible on either C18 or RP-amide phases. It is interesting to note that the phenyl and alkyl selectivity tend to cancel each other out on the phenyl-hexyl phase in this case. This next slide shows a summary of 3 common HPLC method development steps. Although this introductory talk is not about systematic method development, it is useful to briefly review each step. Step 1 is the selection of column and mode of operation. In this example, the reverse phase mode has been chosen as an example. One can choose to screen only C18 and C8 columns. However, important separations can be missed if examples of polar RP columns are not included in the screening process. The next step in the process is choosing the primary mobile phase solvents that work well in an RP mode, such as water acetonitrile or water methanol. While water acetonitrile combinations are often preferred for C18 and C8 columns, water methanol may be preferred for polar RP columns, such as RP-amide and phenyl. It is very important to include water methanol screening experiments when polar RP phases are investigated. The final step is normally an investigation of how additives and temperature influence the separation. Neutral solutes may not require the use of additives such as buffers. However, most acidic and basic compounds will require pH control even during the early screening process. The acenis column line has been carefully designed to produce excellent results for a very wide range of compounds, as suggested in the next slide. When a C18 or C8 column does not produce an optimum separation, a more polar RP phase, such as RP-amide or phenyl, can be investigated without changing the mobile phase. This greatly speeds up methods development and allows simple, convenient automation of the separation process. We prefer acetonitrile storage, especially for polar RP columns, because it is a less reactive environment toward silica than either water or water-methanol mixtures. We also recommend that methanol be explored as the organic component or as a co-solvent with acetonitrile when polar RP phases are employed. In our summary slide, this seminar has provided an introduction to column terms of efficiency, retention, and selectivity that make up the fundamental resolution equation. Some particle characteristics that affect these terms have been described, and a brief introduction to HPLC phase chemistry and separation development has been included. We recommend other Sigma Sapelco seminars that go into more detail on separation mechanisms, column selection, and method development. Thank you.